the session.
Okay, thank you, sir.
The session.
Okay, thank you, sir. So I will,
Yes, sir. Yes, you are audible.
yeah. So actually, what we saw is, wait, I was sharing my screen.
Uh, Sir, may I ask something?
Yeah.
Sir, we do the verification here using System Verilog or UVM.
System Verilog.
Okay, okay, sir. First,
Yeah,
we do the RTL design coding with
yeah.
Verilog. Then,
Today is our RTL design, and then tomorrow we will see uh, that system Verilog verification.
okay.
Yeah, my screen is visible now. You can use comment box also, no problem.
Yes, yes.
As of visible now, okay. Okay. Okay, what we saw previously is RISC-V architecture. Okay, what is RISC-V? It is a instruction set architecture. And then let's go this PPT quickly. Okay, like not like previous session, just an overview. Okay, so what is RISC-V? It is reduced instruction set, and why we prefer RISC-V? Because of its open source and the instructions are somehow easier, simple
Sir,
and easy.
sir, can you please admit few people are joining in lobby?
Yeah, actually, it is showing like admitting, but I don't know why you don't answer me. Okay. Fine. Okay, let's go through this PPT fastly once again, and then we move on to the coding. Okay, so as I told before, RISC-V is reduced to instruction set computer, and why we use RISC-V is because of its open source and it is simple. Okay, simple and easier, and then we there is some advancement. For example, we are using RISC-V. RISC-V in the sense it is of fifth generation. Okay, so this is basic RISC-V architecture. Architecture in the sense, see here in the code also what we are going to do means there is instruction memory. So in that instruction memory, it is going to hold what are the instructions are there. For example, 32-bit instructions. So for fetching that instruction, we are going to use instruction fetch unit. And then for controlling that and sending the data to the ALU and for other controlling purpose, we use control unit. And ALU, we all know it is for arithmetic logic unit. And register file is to fetch the data from data memory, and using that register file, we are going to perform the ALU. And after, if we want to load or store something, we use data memory. And this is the difference between RISC and CISC. CISC means complex instruction set computer. This is somehow the instruction formats are larger and complex, but it have its own advantages, and RISC have its own advantages. And then these are the extensions. For example, if there is a particular format in this extension, inside this extension, we have some other formats like I discussed in previous session. And these are some of the versions like RV32I. It means the instruction length will be of 32-bit, and RV64I. It means the instruction length will be of 64-bit. Like that, I means integer. These are the instruction formats. R means register to register operation, and I means immediate operation, and S means store instructions. So why these formats are there? Because each format have this. Actually, each instruction formats have different format types. For example, for register type, there is some different format like this, and for immediate, it have different format like that. Everyone have its own format. Okay, then pipelining. Why we need to pipeline? Okay, pipelining is used to make our CPU work more faster by overlapping the execution of multiple instruction. If we have 2 or 3 instruction, using this pipelining instruction, we can overlap one instruction by another. One instruction by another means if one instruction is in fetch stage, then another one will be in decode stage. If one instruction is in decode stage, then another instruction will be in execute stage. So like that, by overlapping, we can improve the performance of the CPU. This is what here pipeline is. So there are 5 stages. One is instruction fetch, instruction decode, and one is execute, and one is memory access, and final one is write back. And advantage of fixed length instructions, that is, it is easy to code. As I told in previous session, it is easy for coding, and if we need to locate the next address, if we have fixed length means it will be easier. The CPU can fetch and decode instruction faster because it knows exactly where each instruction starts and ends because of the fixed length. And no need for extra logic. Yeah, obviously we have fixed length means our instruction will be reduced. No, our logic will be reduced. No, that is what they are telling you. And here, simpler pipeline design in the sense, if we have fixed length, then our pipeline instruction, then moving from one stage to another stage, and the next instruction will come into the pipeline. Then these actions, this pipelining function will be easier. Then fixed size means instruction fetch and decode hardware is simpler and more predictable. We can easily predict which address will come next and what and where, from which place to which place. Like that, we can easily predict and easier to calculate the next instruction address. That what I told, and better performance we all know. And simplifies instruction alignment and memory access. So that alignment problem will be overcome when we have fixed length instructions. Then real world applications. Yeah, we all know plenty of companies are using this. No? That is what I told. Like real world applications means plenty of companies using this RISC type. That is what they told you. Then conclusion. We all saw this in previous session itself. Why RISC is this much important and why this is using familiar in all companies like that. So till now there is no doubt. No? In theoretical, apart from coding design, in theoretical there is no doubt. Yeah, you can use comment section also, no problem. Okay, my code is visible now.
Yes.
Okay. Okay then. See, before entering into this coding, I will tell what is our plan actually.
So can you please increase a bit font size?
Yeah, one second please. It's okay, no? Or still I need to. Okay, no? Okay. Okay. Wait, I will tell the plan first.
Sir, so this is Verilog code.
What?
One
second, I will tell you. Okay. Okay, the plan is actually we have 2 codes. Okay, for RISC-V, we have 2 set of codes. One is of 32-bit. Okay, 32i, RISC-V 32i, which have 32-bit instruction, and one is of 16-bit, which have 16-bit instruction. And what we are going to do is we are going to discuss both the designs. And when it comes to verification now, this 32-bit is built of Verilog. Okay, simple and direct verification. When we come to this 16-bit, no, it is built of system Verilog. See, we have some system Verilog architecture like generator, driver, and monitor, scoreboard, So using this, we are going to check the verification. Actually, the plan is I will explain this 32-bit design completely and the 64-bit design completely. But tomorrow we will discuss about the verification. At that time, what I'm going to do is I'm going to explain this in Verilog itself. Better if I have some time, I will try to improve or I will make somehow system Verilog architecture. If I have time and if I can, I will do this. See, or else we have here itself we have some system Verilog architecture. That is what I came to told, like we have verification plan in this. Like if you had an idea like how we are going to verify, then we obviously come across this no. We obviously answer this one also, no. That is what the plan is. Actually, I will explain this. You can also notice that this one and the 16-bit one both are same. So after explaining this 32-bit, I will explain this 16-bit, and you can realize that okay, both are same only. So we can easily understand like that you will feel at that time. So the same for verification. I will explain this verification, this architecture, system Verilog architecture, like why we are using this, what about this environment, why we are using this, and what is happening here. Like that, I will explain. So I will explain this one also, but while explaining the structure, no. So from the structure and the explanation of this 16-bit risk, you can answer this 32-bit risk also. It will be easy only. Okay. So this is what the plan is. It is okay, no? What I'm telling is okay, no?
Yes.
Okay. We will see. Actually, this is system Verilog, and yeah, in while we discussing router project, I think there will be UVM. I think that time we will see UVM, but for interview purpose, no. So that time we need to tell that what we are verifying and how that architecture is. So for that case, I will explain this one, and this design we can use for interview and for verification for this particular design verification we will do using this Verilog itself. No problem. And for this, design will be there and system Verilog architecture will be there. I will explain both also, no problem. Okay then. And finally, we move to this design. Okay. Before going to the design, we are going to check this instruction architecture. See, instruction memory unit, instruction fetch unit, and control unit. And in the data path unit, we have register file, we have ALU, we have data memory. It will be there. So based on this, we are going to see this design. Okay. Okay. The first block is ALU controller. So what is the use of ALU controller? As we discussed, in order to perform some arithmetic logic operation, no, so that we need some control. Like if we in that instruction is of 32-bit. Okay. So in that 32-bit, there is a function 3. Function 3 in the sense it have some binary code like 111. See here, like 111, like 000, like that. It will have some binary code. So we are concatenating that binary code with this ALU operation. ALU OP in the sense ALU operation. That is what operation we are going to perform. So for that controlling purpose, we have this ALU controller. Okay. So this input is ALU OP means ALU operator, and this function 7 now, this function 7 and function 3 is like that instruction. For example, function 3 111 means it is going to do some AND operation. After 111, if have 10, like 111 10 means AND operation. 11100 means AND immediate operation. Like that, function 3 and function 7 will inform us what type of function and what type, whether it is what type in the sense, what instruction format, whether it is R format, right, register to register format, or it is I format, like immediate format, like that. What format we are going to use, that will be told in that function 7. Okay, wait, we will check. See here, this is function, this is opcode actually. Wait, function 7 also I will show. Where it seems. Where it is. See here. So what I told is, see, in this function, there is 7-bit now. This 7-bit will implies like what operation we are going to do. Like see here, they mention no R type. R type I means it is register immediate, like that. What operation we are going to perform, that is the use of this function 3 and function 7. Okay, then finally operation. Operation in the sense what operation we are going to perform, like AND operation or OR operation, that will be mentioned. Okay, so for controlling purpose, for controlling that, we have guests waiting. Okay, waiting. Okay. ALU controller. Okay. So design will be, see, here in the design, there is nothing. We just include the processor, and in the processor, we have all details. No problem. We will discuss. And when it comes to ALU controller, it is going to control the ALU operation. That is what ALU controller is. And as I told, there is 3 input. That is ALU, OP, that is ALU operation. What operation it is going to perform. So it is of 2-bit. And function 7, function 3, as I told you, it is of instruction, like what type and what format we are going to use. And finally, operation is our output. Output in the sense which operation it is going to perform. Okay, this is ALU controller. Then controller. Okay, we have opcode now, 7-bit opcode. So what is opcode in the sense? In that opcode only, we have all the information. Based on that opcode only, we are going to perform the RISC operations. Okay, RISC instructions that is built. Okay, in that format, opcode is the main thing, and that opcode will be changed for every extension. Okay, every extension in the sense for instruction for integer type, we are mentioning like I know. So for that I, there is a particular opcode, and for floating point, what is our that keyword, what is that letter? It is F. Okay. For example, RISC V 32I. So I in the sense integer. So for mentioning that it is an integer type opcode, we use this opcode. So for mentioning like it is a integer based instruction. For like that, and we will mention no, for that we are using this opcode. So in case if we use like it is a floating type instruction, for that we have different opcode. Okay. So that is what they have mentioned here. Okay. And here what we used here is, see here there is one opcode. Okay. So and it will be changed. Okay. We can even you design, you can also customize that. Okay. But as I told you in the previous session, see, even this code is different, this code is different. But the thing is that we should follow the standard, how many bits it should be, and what are the like opcode function 3, like that, what are the frame formats are, like that we should design. That's all. Okay. That standard we should follow. But you can see here, see that opcode is changing now. So for that, see, they have mentioned here now I type operation. So for I type, we have opcode, and R type operation. For R type, we have opcode. Like that, this is the use of opcode. Okay. And in controller, we have opcode, and see, ALU SRC means ALU source. ALU source in the sense which source, from where it is going to fetch. Okay. For that ALU, we are going to perform arithmetic logic unit, that is addition, subtraction, like that. For that, we need source now. Source in the sense where the data is. Okay. Where that source data is, where we are going to get that data. That source now. For that ALU source. And the mem to reg in the sense memory to register. Obviously, from if you are loading or if you are storing some data, we are going to load or store it from memory to register. Okay. So reads write in the sense we are going to write something in the register, and mem read means we are going to read something. Okay. See here, we should notice one thing like memory read. Okay, we are going to read something in the memory. Read write in the sense we are going to write that thing in the register. That is what they have given here. And memory write in the sense we are going to write something into the memory. Okay, and we have seen in the previous block now ALU-OP, that is ALU operation. Okay, and here is the input, that is opcode is our input and remaining are our outputs. Okay, so this is our opcode. So see, it is a opcode which describes like load word. So to load a particular word, there is a opcode. This opcode will change actually. Okay, for loading for this I type, it will change. And when we go to some upper side, no, like integer floating, for that and all, there is some different instruction, different opcodes are there like that. There is some different opcodes. This is the use of opcode, like mentioning what type it is like that. Okay. So if our opcode is like 0000011 means, see it is 7-bit. Okay. So 0000011 means what it is going to do is load word. Okay. So load word in the sense we are going to load something. So what is happening? Memory to rich. So as I told you before, from memory we are going to load something to register. So for loading, what we need to do basically, for loading we need to read. So but for storing we need to write. No, for storing something we need to write that in the memory. But for loading something we need to take the data from the memory and we need to load it in the register. Okay. So for that only we are giving here mem to reg. So what is mem to reg? Memory to register. It is 1. 1 in the sense, yeah, it is going to happen. And memory write. Memory write in the sense it is 0. Why it is 0? We are not going to store anything or we are not going to write anything. Okay. And see here, memory read. Memory read is 1. Why memory read is 1? Yeah, because we are going to read some data from the memory and we are going to store it in the register. Okay. This is what the operation is. And this ALU SRC, no, this is like for that arithmetic logic, for that arithmetic operation, we are going to fetch some source. I will show you how it is working like that. Then read write. Obviously, if we are going to read something in the memory, okay, where we are going to write, it is going to write in the register only. No, for that purpose they have given this. And ALU operation, what type of operation we are going to perform? We see here now in the ALU controller. See this in the register. Here this is register operation now. It is of 2-bit. Okay. So it will, this 2-bit, it will confirm like what kind of operation we are going to perform. Okay. So for like that, we have different opcodes, and for the different opcodes, we have different set of instructions like 0, 1. We have different set of binary instructions. For example, see here, it is like immediate. Okay. For immediate, we no need to like if we are going to pass some data immediately means we are not going to take it from register or we are not going to take it from any data memory. So see here, everything is low, but read write is high. Okay. Obviously ALU source will be high because we need a source, because there only we will have our memory, or it will decide which input should be passed like that. I will show you. And see here, reg write. Why reg write is on in the immediate? Obviously, when we are going to pass something immediate, where we are going to write? We are going to write in this register only. Then only we can perform the ALU or any jump like that operations and all. Okay. So for that, each opcode will have its own instruction. Okay. Actually, opcode is also like an instruction only. But once we are entering into a particular opcode, it will contain instructions like this. Okay. This is what controller is. Okay. it will control. Controller in the sense we all know, no? It will control for this opcode, these and all the instructions, and these operations should be done. This operation should not be done. Like that, it will control. Okay. This is what controller is. Okay. Till now, is there any doubt? Till now, is there any doubt? Or anything you have some doubts or anything you need to know like that? Till now? No doubts, no? Okay. As I told you before, ALU is of a controller which is going to control the ALU operation, and it have function 3 and ALU operation, and our output is the operation. Operation in the sense what operation it is going to perform and or like that. And controller in the sense it is going to control using the opcode, 7-bit opcode. And inside that opcode, it obviously it will have what are the operations should be done and how it should how that particular instruction should happen. Okay. And see, late joiners, no problem. This is recorded session only. I will share the recordings also. Okay. I think, right? Yeah. 4 of you. Yeah. 4 of you here. No. Okay. If you join late or if the call is cut and then once again you join means no problem. I will share the recording immediately. Okay. I will tell the ma'am to share the recording immediately today or within tomorrow. And if you join late, no problem. Listen from this only, this itself. Okay. You can listen from the upcoming blocks itself. No problem. I will explain. And that lifted blocks you can go through using that recording sessions. Okay. No problem. I will share the recording as soon as possible. Then third block, it is data memory. So what is data memory? As I told you before. As I told you before, data memory is like we are going to store something in that and we are going to fetch something. We are going to load something using the data memory. Okay. So for that, memory read. That is, we are going, yeah, I explained to you know in the previous block, that is in controller, memory read. Memory read in the sense, we are going to read something using that memory, data memory. Memory write in the sense, we are going to write something inside that data memory and address. Yeah, obviously it is going to contain some location and that location should be pointed out now. For that, we having address and write data, read data. We all know why write data is for writing something and read data is to fetch something. That is, we are going to read something from that. Okay. With data memory. And here, what is going to happen is you can notice one thing like in this 11th line. Okay. In this 11th line, there is what they told is reg 32 is to 0. So what is reg 32 is to 0 in the sense? And we have memory 128 is to 0. So what it means? Our instruction is that is the each memory location, okay, have 32 bits. Okay. Each memory location have 32 bits. And totally we have 128 memory locations. Okay, that is what they mentioned here. Yeah. Okay, data memory in the sense, obviously we should need some memory, no? So for that purpose, we have 32, actually each location is of 32 bit and we have 128 bits. Okay. And see below we have read data. It is easy only, no? Okay. So before writing or before doing something, we are going to make all the registers to 0. Okay. Then only we can store, not like that. We can store also, we can store something, but for our preference and some prerequisite, it like, okay, we are going to make all the instruction to 0 and then there will be a write or read operation. And you all know, see here, memory write in the sense, Wait, I will open my first painting. Okay, see, memory right in the sense, here is our memory address. Okay, address in the sense, it write data. Okay, so here, this address, no, address in the sense, it is going to handle some address like 64th place, this like 64, 32, like that, or 10, 12, it is going to have some address, okay, which should be above 0 and it should be below 128. Okay, so for example, if you are going to write some data, okay, if you are going to write some data like in the memory location, then I need to write a data which is like 134 or 123, like that. Okay, like 125, like that. If we need to write something, we are going to use this. Then if we are going to read something, no, if we are going to read something, what we are going to do? We are going to read data. Okay, read data from a memory location. Okay, like 10. That's all. So what we here, what it will happen? So in this 10th memory location, there will be a data. What data it is? 125. So that 125 will be read. Okay, this is what read operation and write operation. Okay. Okay then. See here, they are also doing the same only. Okay. If the what here they do, what here they are mentioning is, see here, if read data, okay, it is high, then in that particular address, it is going to read some data. If it is low, obviously our 32-bit will be 0 because it is low means we are not going to read anything. Okay, that is what they are telling here. And next one is flip-flop. And you can ask a question like here, why we need to use flip-flop like that? You may have a question. Okay, so we use D flip-flop here. Here, the use of the flip-flop is to carry PC. PC in the sense program counter. Okay. So program counter in the sense, what is program counter? It is going to hold the address of the next instruction, which is going to be performed. Okay. So that is why we are using D flip-flop. What is the use of D flip-flop? It is data flip-flop. So obviously, what we are going to give in the input side will replicate in the output side without any change. Okay. So if we pass a PC, that is program counter in the input side, it will be replicated to the output side. Then you can ask me, then why we need to use this flip-flop like that? You can ask. The reason is, or we are using clock. Clock in the sense, we need to send our program counter, we need to execute our next instructions in a synchronized way. Okay. And if we need to reset, we should have some signals. Okay. So for that purpose, this D flip-flop will be a suitable one. Okay. So see here, on the passage of the clock, if reset is Q will get 0 for a synchronous reset. So basically, this flip-flop is for transferring our program counter's address. Okay. Obviously, program counter will hold the address of the next instruction. But instead of, if we pass means we can't pass in a synchronized way, no? So there should be some device which should pass that PC in a synchronized manner. Okay, in a controlled way. That's why we are using flip-flop here. Okay, that is in D flip-flop, we all know data flip-flop. Obviously, what we are giving in the input will replicate in the output. Okay, the same will come in the output side as well. Okay, then next one. Okay, till now you all understood, no? There is no doubts, no? Which are the blocks and why we are using this? What is the purpose of that block? Like that you can understand, no? Till now is there any doubt? You can ask. Till now we completed till flip-flop. Okay, we have completed 4 blocks. Till now, is there any doubts? No doubts, sir. So we can pass to the, you can use comment session, comment box also, okay? I'm available in that also. Okay. Okay, next we are going to move to the generate, immediate generate, okay? So as we discussed before, we are not only going to pass the data through register, or we are not only going to pass data using some memory or some load store, okay? Obviously, we are going to pass immediately also, okay? It is also available. So for that purpose, we need to use immediate generation block, okay? Here there is inst code. What is this? It is instruction code, okay? Instruction code in the sense, we will pass some instruction, no? In that instruction, there will be some information about the immediate data. Immediate data in the sense, we will pass some address, we will pass some data, that instruction, okay? That instruction code will code that immediate generation instructions, okay? So this immediate generator will generate the immediate value based on the instruction code, okay? So here, okay, here it is like we have instruction code and we have immediate out, okay? So then this why we are using register here is it is nothing but we need some storage space now. So for that purpose we are using register, that's all. And see here at always at inst code, okay? Here what is happening? We are giving some code here, and see it is a 7-bit code, okay? This, that is instruction code is a 7-bit, okay? See here each code have different operations, okay? Here it is immediate addition, like that we have. And you can have a question like, why this immediate out? What is the use of this? Like you have some questions, no? If you have some questions, the answer is like, see, here is they are checking inst code 31. So what it is 31 in the sense, the MSB bit. Why we need to check this MSB bit? Whether why we are checking is, we are checking whether this MSB, okay, it is signed bit, no? So if it is a signed bit, so we are going to check whether it is a positive or negative, okay? And one more thing is, if it is positive, we need to extend the remaining bits with 0, and if it is negative, we need to extend the remaining bits with 1, okay? So here it is of 20 bits, okay? Okay, see here what they did is, here inst 31, if it is 1, okay, that is if it is negative, the remaining 20 bits will be negative only, no? So we need to pass this remaining 20 bits as 1. So if it is positive, we need to pass this remaining bits as 0, okay? This is the operation of this. This is the instruction that immediate outs work, okay? It will have some instruction code that how the immediate data will be generated, how it is passed, and then we need to extend the remaining bit, okay? If it is positive, we need to extend it as a zeros. If it is negative, we need to extend it as ones, okay? This is the use of this immediate generator, okay? Then here, till immediate generator, you can understand, no? Is there any doubts still now? Or anything you difficult to understand, or any doubts like that? If you have, you can ask till now.
Hello. Sorry, I
Okay.
joined late. So, just can you briefly tell
Yeah.
about the block, like immediate generator,
Yeah.
controller,
Okay.
like that?
I will
Just
explain in a short way. Okay. For
yeah,
your
in a
right
short.
now, for this understanding, and for
Yes,
some brief
please.
understanding, you can go through that recordings. No, I will
Sure,
send the
sure.
recordings as soon as possible. Okay.
Yeah,
So
yeah, sure, sure. Thank
till
you.
now, what we see is it is ALU controller. ALU controller is obviously we are going to do some ALU operation like and or nor operation like that. No, so to control that ALU operation, like which operation we are going to perform, and this
Hmm.
function 3, no, this function 3 and function 7, these two are like a instruction. Okay, That function 3 is a 3-bit instruction and function 7 is a 7-bit instruction. Okay, where you see this
Okay.
function 7 means it is from so here you can see. Okay, wait, I will show you. Wait, we will come. I will show you.
Yeah, yeah,
So
sure.
so using this function 3, it is an instruction. Okay, see here also 111, here also 111. Okay, so 111 is a some instruction. So after that, okay, ALU OP means ALU operation. That will decide in that function 3 what operation we are going to perform, like and or and I means and immediate. Okay, like that. To control this ALU operations, we use ALU controller. And this controller, no, it will control generally, like we have a opcode. Okay, opcode in the sense in the instruction set, the opcode is the main thing. Okay, it is going to decide whether our instruction is going to perform I type, that is immediate type, or it is going to perform R type. R type in the sense we are going to transfer, that is the data transaction will going to happens between the registers, or how it is going to happen. So while happening, like if we are performing I type operation, what are the signals should be in off state and what are the signals should be in on state. So like that, for controlling everything, we use controller. For example, if there is load operation, no? So if we need to load something, what we need? First we need to, why we need to load something? We are going to load some data from memory to register. Yeah, in memory we have some data. Obviously, we are going to load the data into the register. Okay. So for loading purpose, we no need to on this memory write. Why we no need to on this memory write? Because we are not storing anything here. We are just loading. Okay. But why memory read is on? Yeah, because we are going
Loading.
to read something from the memory and we are going to write something in the register. Okay. ALU SRC in the sense ALU source. Okay, source in the sense obviously we have some source, we have some destination. No? So I will see in the I will show in the upcoming code where that source is and how that source is selected. For example, there are two inputs. One of the input we are going to select. So for that and all, we need source. Okay, and this register write. Why this register write is on in the sense after fetching some data from the memory, we are going to write that in the register only. For that register signal, register write signal should be in the on state. Okay. So for like this, if we need to control, like for this opcode, this signal should be high, this signal should be low. For this controlling purpose, we are using controller. And data memory, we all know we are going to store something and we are going to load something using this data memory. That is the operation of this data memory. So here our data memory is of each location is of 32-bit and there is totally 128 memory locations. Okay. And before starting, we are going to make all the locations as zeros and then we are going to perform this write operation and then we are going to perform this read operation. And for that, I showed you an image. See here, for example, if we are going to write something here, for example, memory 10 is equal to 125 means we are going to write that 125 data into the memory 10. It is just an example. We no need to confuse with this with that risk. Okay, I just wrote you what that read, write, how the data memory will act. For that, this is a small example. Memory 10, we have 125. That is, we write some data in this 10th memory. Okay, and to read that, we are going to like read data is equal to memory 10. That is, in that memory 10, we are going to have some data and we are going to read that data. For that purpose, we use data memory. Then flip-flop. Then why we need flip-flop is there is PC, program counter. So what is the use of program counter? It is going to it holds the address of the next address, the next instruction. Okay. So next instruction we have now. So that address will be held by this program counter. So our program counter's address should be same. So here we use D flip-flop. Why D flip-flop means data flip-flop. So whatever we pass in the input, the same will come to output as well. So why we need, we can directly pass that we can directly pass the next instruction. Why we need this flip-flop? Because for synchronization. Okay. So if there is a program counter waiting, so in a particular clock period, it should come in, and in particular clock period, it should go out, next instruction should come in. For that synchronization purpose, we use flip-flop here. And then register immediate generation. Why immediate generation? Obviously, in REST-V, we are not only we are going to perform like register operations, and we are not only going to perform that ALU based on the registers. We will pass some data immediately also. So for that immediate generation. So this immediate in this immediate out, there is like instruction code 31. So what it means? It is if it is a signed bit, obviously that MSP will hold that what sort of sign it is, like 0 or 1, like that. Okay. If it is 0, then it will have, if it is 0, then it is positive. Then we need to extend. We have some remaining space now. Obviously, here our immediate instruction is a 7-bit. So even though we use some other bits also, we have some remaining bits now. So that remaining empty bits should be filled based on the sign, what sign that hold. Okay. If it is positive, that is what they are telling in this line, that if the inst 31, that is if our MSB is 1 positive, then our remaining bits should be filled with 1. Or if it is negative, then if it is negative, our bits should be filled with 1. If it is positive, our bits, that is the remaining bits should be filled with 0, and continuing with the instruction code. That is what this immediate out is of, and it will have the immediate instruction. In immediate, we have different types of instruction, but this is the format. This is what this immediate generation is of. Okay, till now you understood, no? Someone asked me.
Yes.
Okay.
Yes.
Okay, sir. From
Thank you for
here
that.
onwards, no problem. From here onwards, we will discuss. Okay, instruction memory. So this is the base one. Okay, this RISC-32I will hold 32-bit instruction, and this 32-bit instruction should be stored in some place. No, that is what this instruction memory is. Okay, so in this instruction memory, all the, see here, actually here we have 64 memory locations, each of 32 bits, but for our purpose, we are using only 19 locations. Okay, if you need to customize in future, you can use this 34 memory locations also. Okay, so as of now, we use this 19 locations. Okay, so see here, the instruction code, that is the RISC-V will execute based on this memory only. So what this memory is containing? It is containing a 32-bit instruction. So this 32, wait, see here, we were to, here it is. Here is a frame format, no? So see, obviously if you count means after adding this, you will get 32-bit. So same here. Based on this 32-bit only, we will split everything like function 3, function 7, opcode, and what type of instruction, what type of format it is. So everything will be considered, and everything will be splitted based on this instruction only. So, okay, this is the use of this instruction memory. And obviously this instruction memory is having an address. So what is the use of this address in the sense? It is a memory location. No? So obviously it will have some memory locations. Like here it is have 64 locations. For locating that, we need some address. No, that is what this address is of, and instruction. So it is output, because finally, why we are using this instruction memory? We need some instruction. What that 32 instruction, that 32-bit instruction. Okay. Finally, we need that 32-bit instruction. So for that, we are using this output signal as 32-bit. Okay, 32-bit instruction. See here, they are assigning here. So you can notice like address of 7:2. Yeah. Here also address of 7:2. You no need to confuse, like in that particular address. Okay, we have that 32-bit memory. That is what. But we in the whole purpose, okay, our instruction will be of 32-bit only. We no need to confuse that. Okay. So here in the next block, okay, till now we have completed this instruction memory, and Instruction memory, as I explained, it is going to hold all the instructions, okay, 32-bit instructions. So based on this instruction only, we are going to perform the upcoming operations and all, like operations, function 3, op 4, everything will be contained in this instruction memory only. And then this mux2. Yeah, then you can ask, what is this muxes of? See, previously I told you, no, there is ALU source. So that source is this mux only. See, there is two inputs, that is data 1, data 2. And this is the source, okay? From this source only, obviously, if we have two data, we can use this two or we can have any one, okay? So for that, we need some selector, no? For that selection purpose, we are using this mux here, okay? And this mux, no, its main purpose is that we discussed like ALU source, no? So that ALU need a source. So that source should be a data. That data will be selected using this mux. Okay. This is what this source is of. Okay. So once again here, yeah, what is the use of mux? It is like a data selector. We have two data and that two data will be selected using the select line and our output is y. Okay. So this is what like assign y is equal to s question mark, it is they are using some conditional operator. Okay, right, like ternary operator we told, no, like we usually tell it like ternary operator, no, they use like if our select line is 1, obviously d2 will be selected. If our select line is 0, d1 will be selected. Okay, this is what this mux block is of. Then register file. Yeah, this register file is it has some input signal. Okay, I will first decode that, like what are the signals are there, what it is of. Okay, like RG write WRT EN, that is you all know, no, write and register write enable. Okay, then we have register read address 1, register read address 2. Why we are giving address 1, address 2? See, you can customize, okay, from our side in this code, in this arithmetic, in this ALU, we have two inputs, okay. So if we are completely based on this register operation, then we have two inputs. We should have two inputs. So that two inputs will have some address, no? That is what register read address 1, register read address 2. Then we have register write address. Then we have register write data. Then we have register read data. Then we have register read data 2. Okay. So we have two address. So for that two address, we are going to fetch something new. That is what they are telling here. Okay. That two address will contain two data. Okay. That is what register read data and one that and register read data 2. And see here. And these and all, you know, no, clock reset and all, what is the purpose like this. And here it is also a 32-bit and our register there is, see here there is 31 location. Okay. But we are using 2. That is what I told. We can customize. Okay. This is the code, basic code. If you need to customize, you can. Okay. After this session, I will send both the codes. Okay. You can refer both the codes also. Okay. So see here, it is like, first of all, what we are going to do, we are going to reset. Okay. That is what they are also doing. And as I explained you before, we want to write something, it is like register write address is equal to write data. This is that we are going to write something inside the register. If we need to read, what we are going to do, read register read data, and we are going to mention that register with the location. That is in which location we are going to fetch the data. Okay. So finally register file is up. We are going to load and we are going to store something in the register. That is what the operation of the register file. Okay. Till now, you all understood, no? Like this each block. See, you can understand, no? Each block having some purpose. Okay. So till now, you have any doubts, or you have like which for what this block is using, like that? You have any doubts? Till now, everything is okay, or is there any doubts? You can ask now. Is there any doubts till now? No doubts, sir.
No, sir.
Yeah. Okay. Okay. Uh, yeah, from my side it is okay. For you, I will send the code. You can also go through it. Okay. Even for someone, it in a single go, we can't understand. No. Yeah, we can understand, but not in a thorough manner. Yeah, you should practice. I will send the code. You can go through. And the next one is ALU 32. See, ALU 32 is not like that. You don't need to confirm. ALU, you don't need to confuse. ALU 32 in the sense ALU, which is of 32 bits. That is what we are just mentioning here. Okay. So module ALU 32. Okay. Then here we have see 2 bits. Okay. One is A. We have 2 inputs now. Obviously in a ALU, as I told you before, here in this code, we are going to perform based on 2 inputs. Okay. So we have A input, we have B input, and ALU select in the sense what operation we are going to perform. Okay. Previously we see that, and ALU out is our final result. Okay. Here carry out and overflow. See, we have a MSB. So that MSB, after our MSB, there a bit will be generated. No, that is carry out, and we have a particular range for 0 is to 32. There will be a range from this number to this number, like that. If our operation crosses that number, no, then overflow bit will be activated. Okay, that is what this full logic is of. Okay, see here we have ALU result and that temporary register and all we have, no. Then ALU out is equal to ALU result. Okay, ALU result is our ALU out, and ALU, if see why they are assigning 0 means finally our ALU should be 0. That is, after completing the operation, we need to perform some next operation, means then our ALU will be 0. No, that is what they are mentioning here. And initially our overflow is 0 and our carry out is 0. Okay. Then ALU select based on our, we will see in the top layer, we can notice like where these signals are all connecting. Okay. So we will see in the next blocks. Okay. So here initially our overflow and our carry out, these both are 0 only. Okay. Then here it is like ALU select. Okay. So if all the 4 bits are 0, it is like AND operation. It is going to perform AND operation. So you can understand now ALU select in the sense it is going to select what operation we are going to perform. And this ALU carry, see here, carry out in the sense this final 32nd bit. Okay. If it is 1, that is what carry, no? After completing, if we are adding 2 inputs means it will produce some, if our MSB is extending and it is produced 1 means it is considered as carry. Okay. For example, in half adder, what we do in half adder, basic half adder, both the inputs are 1. Our sum is 0 and the carry is produced. No, same here. This carry also same only. Overflow in the sense, see, we have some sign bits. No, in that sign bits, we have some ranges. Okay. So if our input, okay, after final result, if our result is exceeding from that particular range, then this overflow will be activated. Okay, this is what this ALU is of. It is going to perform some ALU operation, and based on the result of that operation, it is going to generate carry and overflow. Okay, wait a second. Okay then. So as of now, we come across with this ALU. Okay. Okay then, data path. Data path in the sense, see here, where's this? In this architecture, okay. See data path. Data path holds ALU and register file. Okay. Inside this data path only, we are going to configure. That is, we are going to instantiate this ALU and register file. See here, everything. See, register file is instantiated here, mux here, and then immediate generation, ALU 32, data memory, mux, everything is instantiated in this data path only. Okay, so you may ask the question like there are different signals, but overall, if we consider means somehow one signal should be connected to another signal. For example, see here, if there is a register file, okay, we can consider it as, see here, this is mux, okay. So what is the output of mux? It is ALU in 2, okay. So this mux, okay, this 2:1 mux output will be connected to this ALU input, okay. Why? Because this ALU needs some source, needs some data. So who is going to select the data? This mux, okay. It will select the data and that will be performed in this ALU. See, this mux output is connected to the ALU32 input, okay. Same, you can compare like, see here, wait, I will show you. See here, in this mux, there is a write data, okay. Wait, let's consider this as variables. Okay. See here, this data memory is giving us a read data here, okay. This read data, it is output here and it is connected as the input to this mux, okay. So why this top layer in the sense? All the signals, no, we are going to connect with one another because in this layer, consider this layer. Here there is instruction memory. Obviously, this instruction memory will be fetched using an instruction fetch unit. Okay. This instruction fetch unit will be sent to the data path. Why? We will select something new. So this instruction fetch will be controlled. Okay. It has some instruction. It will be sent to the control unit and some of the data will be sent to the data unit as well. Okay. So for that purpose, we need some connections. Okay. See here, page. One and one, see here. There, each block is connecting to each other, no? So for that purpose, we need this overall layer. See here, each signal will be connected to one another like that. Okay. See here, we are mentioning like opcode. Opcode in the sense, see, first 7-bit is opcode, and from 25th to 31, it is function 7, and from 12 to 14, it is like function 3. Okay. They are assigning here, that's all. This is the data path. Actually, you can understand, no? Here we are just connecting. Each block should be interconnected with each other, no? So that connection is made here only, okay? Then DP top in the sense data path top, it is going to contain some information regarding this data path, like what type it is, R type, and ALU, that is load word, then store word, and here there are some other informations, okay, regarding this data path, okay. So data path is a block. So to control that data path, there is a top data path, okay. That is what DP top in the sense, okay. See here, if our opcode, here there is opcode and what type it is, if it's like what they are telling here is, if our opcode is equal to R type, okay, and our opcode is equal to R type I, that is R type immediate, register type immediate in the sense, our function should be like this, okay. And if our function 7 is like 7-bit fully 0 and our function 3 is fully 0, what is our output is 4-bit 0010. Else it will produce this opcode like this, okay. Okay, can understand, no? Overall, so to control that data path, we need a data path top. That is what they are mentioning here. They are instantiating this data path and they are giving some information regarding that data path's operation. Okay. So finally, this processor. Okay. So what is the use of this processor is, it is going to hold all the major blocks. What are the major blocks? Data path and that controller and that ALU controller. So it is going to hold the major blocks. See, in this data path, some subblocks are here. We are instantiating some subblocks. Okay. like immediate generator, ALU32, data memory like that. And in the processor now, it is going to hold the major blocks. Okay. So here also you can notice like, see here, ALU-CC in the sense, ALU, ALU code. Okay. That is ALU condition code. Here in the ALU controller, ALU condition code, that is operation. Okay. It is output. And see here in this data path, it is given as input. Okay, like that. In the ALU controller, we have function 3. Here it is producing as input. Okay, this function 3 and function 7 is produced, output is produced by data path and it is given to this ALU controller as an input. Okay, see here, we have input now here and see this data path. We have outputs now like function 7 and function 3. Then how it will connect? It will connect using this processor. We are instantiating that major blocks and we are connecting. This is what happening here. Okay. Then all this processor, okay, will be taken to this design, and in this design we are just going to include that library alone. Okay. You can include, or if you know it, you don't need to include this. Okay. This is what RISC-V32I operation sub. See, once again I am telling, it is a type, it is a sample. Okay. If you need to customize, you can customize. Okay. For example, see here in this data memory. Wait, I will show you. In this instruction memory, they are using 19 instructions. Okay. But there is some space like 64. There are some 64 locations. If you need to customize, you can customize. Okay. This is what RISC-V is of. Till now, you can understand, no? Is there any doubts till now? Till now, is there any doubts? If there is any doubt, you can ask. No doubts, sir?
In
Yeah.
the processor.sv, can you please?
Okay, okay. Yeah.
Like I understand that we are connecting the different blocks here.
Okay.
Just that not in the processor as we before that we have used some other also, right? In the data path or
Yeah.
.sv.
Yeah. Actually, see
Yeah,
why we
so
are. Oh, yeah. Yeah.
so
Continue.
like how we get to know like okay, this is an input to this or this is an output to this, because just we are connecting that
Yeah.
here.
Yeah. Yeah. That connecting it itself. See why we are connecting just to imply. See here. This is data path. Okay. So here we have mux. So
Yes,
this must have some ALU result. Okay. So
yes.
this ALU result will be produced by some blocks. No. So wait, I will show you. We can see some example also. Wait, I will.
I mean, is it a sequence like first the inputs are written, then the outputs are written? Like in
No,
the
we
Mux
are just
21, Mux 2. Uh,
instantiating. This sequence is, see, in the mux, in what order we give this no? Like
yeah,
D1,
yeah.
D2, select line, Y.
Yes,
So
yes,
this
yes.
same order should be followed. But why this they are giving like dot D1 in that bracket like RG dot data, no? So this register data is the input signal here. Actually, this data path have a some input signal, no? So this data path's input signal is like that register. Not only in data path, in some other block also we have RG data. Okay, so that RG data is passed in this mux. In this mux, we have D. Okay, so wait, I will show you. See, this is basic mux. Okay, this is two inputs and one output and one select line. Okay, so according to this mux, okay, this is D1. Okay, and this is D2. Okay, but we should pass some input, no? So how we will pass means by connecting this using some they
Okay.
have mentioned, they have mentioned like register data, no? So we will connect this to this D1 by wait, we have to by using this format. Okay. So dot D1 in that bracket RG data in the sense in that D1 in place of D1 what we are connecting is this RG data. That is what it implies. Like that only we are going to connect this input. That one signal's input to this one. Like that we will connect. Okay, now
Okay.
still any explanation or still you can't understand this thing?
No, that
It's okay.
only. Just I'm asking that, like for example, I'll take ALU 32 A1 dot A dot B A dot ALU select dot ALU out. Is the base
Okay.
the order is written in the whatever it is like in the design input output like that only, right?
Yeah. See, actually here, this is the basic design, no? Yeah,
Ha ha ha.
what we usually follow is first input, then output. That is what
Then
we
output.
usually
Yes.
follow. But
Yeah.
in some case, if we write like here, if we write output, and here
Output
if we
then.
write input in the case, then in this data part, we can write like here we should write in the out. Here we can write output, and here we can write input.
Yeah.
Like that also we
So
can write. But in this place, we are using like dot memory write. See here, dot memory write, memory underscore write. So this
yeah.
dot, no, this format, particularly this format, what it implies is if we change the data, if we change the place also, like instead, how I am telling is, see, here this memory read is in input. This is a input which is located in the first place. Okay. In
Yeah.
this place, if we write this memory in some other, see here, we write this in second place. Okay.
Second thing. Yeah.
But how it will connect is this format like dot mem read, memory read in the sense it will directly go to this memory read, that is data memory, and it will take that memory read, and instead of that memory read it is going to replace with this small memory read. Okay, that is
Yes.
a
Yes.
format, it is an expression format. If we no need that for example, wait, where it is.
So the order matters or not? That is my question.
Yeah, that order matters, but the way of execution, how we are executing that order. See, wait, I will show you that example. See, let's consider this memory. Okay, module memory. Okay, let's consider like we have some D1, D2, and we have some W slash or we have some read, right? We have output. Okay, this is a top layer. You consider this as a main block. Okay, if we are instantiating, this means what we do memory. We will give some name for that, and see there are two types. One, if we have some other signals. Okay, see this is one module, and in this module, no, wait. In this module, no, if we consider this as a separate module, this as a data path like that. This is example, okay, for your understanding I'm writing. Okay,
Yeah.
if this is a data path and here we have R1, R2, and we have some other R, right, we have enable, we have out, like that. It is the here means while instantiating, okay, there are two types. One is based on the place. See R1, R2, and we are writing R, we are writing W, and we are writing out. Wait, this
Yeah.
out will be like out one, like here also this R1 will be like R1, R2. So what is here out one, right one, R1. Okay, so the same signals only, but that place. See here, this is these place and these place. It will compare. Okay, in the place of D1 there is R1. Then that compiler will take like okay, in the place of D1 we are going to give the signal R1 signal. Like that, our compiler will calculate. This is one format, and here we use no like dot R1. And here, if we use like this means what it is, even though we are changing the place, okay, like R2 dot R2, in the place we are using D2, okay. So even though we are changing the place, it will consider,
But yeah.
it can locate that using, this is a format, okay. Using this format, it can locate. This is a type and this is one type and this is one type, okay. There are two types. Okay, basically why we are using this, even though there are plenty of signals, no, so we may dislocate and write in some case. So in that case also, our signal should be properly, it should be interfaced to the proper place. So for that purpose, we use this one, okay. Or if you are confident with your signal, yeah, I know first place this signal will come. If you have the confidence, means you can just like, you can write like this itself, okay. It is like a format only, okay.
Yes. Okay, got it. Thank you so much.
Okay, now, okay, see here, now we are going to see one more code. Actually, I'm not going to explain this much detail because you will yourself have some idea, no. Now I explained you one code and I'm going to explain the second code, and you can notice like there are some changes but the same operation, okay. See here in design, we just included, okay, we just included this processor, and in processor we have these purpose, we have these blocks and all, okay. But here, see, in the design itself, we have all the important blocks, okay. That is what I told you before. We can customize and we can write the code according to our need, but the thing is we should follow some standard, that risk standard, like opcode is there, like that and all, and we can write, okay. Here it is a basic code, okay. So we no need to worry about that. I'm just telling you there is a code like this also. We can write like this one also, okay. See here, ALU, as I told, ALU is for arithmetic logic operation. See, in the starting of the session, I told you, no, you can understand. If I explain you one program is, when it comes to second program, it is similar only. So you can easily understand. Okay, like ALU in the sense, it is going to do some arithmetic operations, logic operations. See here, same two inputs and ALU control is here. And see that operations, like if we have 000, it is like add operation. If we have 001, it is like subtraction operation. Like that is for ALU. Okay, you can understand, no? Previously in the previous code, what is there? The same is here. Okay, and 1 second. Okay, see data memory. You are familiar with, no? We have in the previous code we have explained, no? Only the structure and the bit and the implementation of the code, it will change, but the overall layer, no, it is same only. You can easily understand. Okay, data memory, same operation. See, that signal name may change, that is depend on the designer. It is in the designer's hand and the implementation is in the designer's hand, but the concept is same only, no. You can also understand that. See here, same memory access, same memory write data. What we are going to do with memory write data? We are going to write something. So we are going, in order to write, we have enable here. That is only when the enable is on, we can write something. Okay, we can write some data inside the memory. Then we have memory read and memory read data. And see here, this column they have given like this,
Sir,
no?
sorry to interrupt. Sir, can you
Yeah,
please add someone is lobby? I think Vinita
yeah.
is in.
Okay. Yeah, okay. Okay, here. See, you can understand, no, this code is same here as well. Okay, that structure you can, I think you can understand that structure here. See here, the same is happening, and this column, no, column and row, why they are doing like this means, see, in the parameter they have defined column is of 16-bit and row is of 16-bit. So just we are taking here what the implemented, that is we are taking here the defined one. Okay, see here, we included this parameter, that block we have included here, and we are just defining the inputs. What we defined there, we are just taking that name alone. Okay. So same. What, see here, this test data. What is this test data in the sense? See here, we have some, where is that? Here, the test data. So this data we are going to use as a test case. Okay. So this data is used as a test case. That is what we are given here as test data. You can understand, no, see, this, we are just including this block, that's all. And as you know, register. What is the purpose of register? We are going to read something in the register, or we are going to write something to into the register, or we are here we have register read address. That is, in a particular address, we are going to write some data inside the register. The same operation. What is that? Here also same only. See, reg write enable and reg write data, reg read data, address one. Same here. Here also two data. Okay, data one, data two, address one, address two. That place and the signal name will be changed. Will be like little bit. It will be modified. See, the same here. If you need to read something, reg array and the particular address, that memory location. Same here. And if you need to write that reg array, that particular memory location, that is destination, we are going to write our data. Okay. Same. And the parameter I told you, know. So instead of using in every place, instead of using 16 like that, we have some name. Okay. That is what this parameter, and we defined in this block. And the data path. There also we see, same process. We see here. Here also they have implemented. See here, instruction memory and mux, they have implemented. Yeah, that is instantiated. The general purpose register. General purpose register in the sense, there we have some register memory, no? Same here. Okay. And there are some immediate extend multiplexer. See, same. We are extending register memory here. As I told you in the previous code, here we are going to connect the signals. One block's output signal will be another block's input signal. For example, here this memory, instruction memory's output, okay, is the input of this instruction fetch. Okay. So this instruction fetch unit's output will be the input of the data path unit, and it will be the input of the control unit. So there we are going to define that input output means here only we are just instantiating, and see, we are connecting using this. No, one signal's input will act as another signal's output. Okay, I will share you the code. You can go through it so that you can understand more easily. You can understand more deeply. Okay. And control unit, as I told you, here see, they are using 4-bit opcode. They say load, see here, some store word, load word, same operation, data processing, same only here also. Okay. Yeah, see here, there are plenty of operations, no? See, same, that control unit, what I told you in the previous code, control unit will have what the opcode is and which type it is, and we enter into that opcode and we enter into that particular operation, which are the signals should be on and which are the signals should be off, that which are the signals should be in high state and which are the signals should be in low state. These things are mainly done in this control unit. Okay. Then test data, that is what are the data we need to test. We have some separate blocks, and here see ALU like addition or subtraction. For that control, if you are going to do some addition, this will control that ALU block. Okay, based on this ALU will work. Okay, and we are going to control this overall, this overall signal. See here also mux. Okay, for the data selection, there is mux here, and this overall signals will be controlled in this design layer. Okay, we are going to instantiate some main and important blocks, major blocks, and here we are going to connect the signals with each other. Okay, this is what the design is. Same. What is I explained here? Same here. Okay. So this one you can understand, no? Like this block is for this. and there is some set of signal. This purpose is like this only. Like that you can understand, no? For example, register address means, okay, we are going to point some address inside that register. We are going to write something inside that register address. Like that, you can compare these two codes and you can understand, no? Everyone, you can understand, no? Till now. Hello?
Yes, yes.
Okay. And throughout this session, my screen is presented, no? My voice is also good, no? No problem in that.
Yeah, no problem.
Yeah, okay. And yeah, I will send the both the codes. I will send both the codes. You can go through and you can also compare, and so you can learn somehow deeply. Okay. And see, one more thing is you can search some code as well. Okay. There are many open source platforms. I think I no need to explain, you know. So for your purpose and for extra learning, you can go and search in some GitHub. There are plenty of codes. You can go and take and use that also. Okay, no problem with that. We no need to use in the sense you can use that for referring. Okay, for some referring purpose, for some extra learning, you can use that also, and you can use these codes as well. I will send these two codes. Okay. I will tell ma'am and I will send the recording sessions also. Okay. So as of now, if you have any doubts, you can ask. Do you have any doubts till now? No doubts, no? So if you have any
Like
doubts, yeah. Yeah,
I couldn't join the first session of this, so can I get that also? Like
yeah.
first.
I will share every recordings. Okay.
Sure, sure.
Okay, someone uh, unmuted, no? Some doubts, anything? Is there any doubts?
No, sir.
Okay. If you have any doubts, you can ask or you can leave. Thank you.
Thank you.
Yeah, thank you.